somewhere over the rainbow.
Hi, I'm Kate Bowers.
And I'm Matilde Garcia.
And today we'll be talking about why a rainbow is polarized. Okay, so a rainbow works because you have light from the sun comes in and hits this raindrop. It refracts at this air-water interface and it disperses as it comes through here. It reflects again at this water-water interface and it disperses some more, and then it refracts and comes to your eye. Because of this dispersion that happens in the rainbow, that's why we see that spread of colors that we call the rainbow. So why we expect this to be polarized is that this light coming in here reflects at the back surface of the raindrop at about 40 degrees. So the Brewster's angle of this water-to-air interface is at 36.7 degrees. So because this is about 3 degrees offset, we expect the light coming out to be heavily S-polarized, or to have its electric field vector oscillating normal to the plane of incidence. Because at Brewster's angle, we expect the P-polarized light to be mostly transmitted through. So we're not quite at the Brewster's angle, but we're almost there, so we expect it to be mostly polarized. So if we use the Fresnel equations at each of these interfaces and times their products together, we find that the light coming back to your eye should be, the S-polarized light should make up 96.6% of the light, and the P-polarized light should make up 3.3% of the light.
So we have our setup for the experiment, and here we have a mister and we have a floodlight. The floodlight's at a higher place to simulate the sun, and what we're doing is recreating a rainbow. So if we imagine the floodlight is the sun, it's coming at a certain degree. For us to be able to see the rainbow, we have to go down, and then we can see the actual rainbow.
Okay, so then the floodlight creates about a 42-degree angle with the water and where we put our camera, and we use a color USB camera to record the colors from the rainbow and the relative intensities. Okay, then after we record the default rainbow, we put a polarizer oriented both horizontally and then vertically in front of our camera to see how the polarization changes.
Using a picture of the rainbow as seen through the fluorescent film, we use the MATLAB code to find the average values of the red, green, and blue pixels. And we squared them and then added them together, and then took the square root of that to find the average intensity of the light as seen in the picture. We normalized the data of the red, green, and blue values by taking a picture when there was no rainbow there, and then we subtracted the red, green, and blue values of this picture from the other ones. From our normalized data, we found out that the vertical polarizer transmitted only 5% of the light, and the horizontal polarizer transmitted 95% of the light. Why our values don't exactly match up is because our axis of polarization changes along the bow of the rainbow. Okay, so in our picture we would have a small spread of the direction of the S-polarized light.